Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Yeah, we are still discussing about DSP, which is digital signal processing, and now we have so far done 2 chapters. So today we are going to begin with a new chapter. Of course, it is a continuation of what we have seen before. Today we are going to discuss about the discrete Fourier transform. But before that, there is a quick review of what we saw in the previous chapter, which was Z transform. Last time we discussed about what is a Z transform and what is it in details and what does it help in terms of signal processing. And we discussed also the types of Z transform. We also saw some of the properties of Z transform. We discussed poles and zeros. Remember poles and zeros, the numerator being zeros and denominator being poles. So we also discussed about the relationship between the tabulation, how does it get related with frequency and time domain. We also discussed about the inverse Z transform, the other way around. We discussed about the convolution sum. What is convolution? You remember all the things we discussed about them. We also discussed about the correlation and so on and so forth. Those are the quick reminder of what we discussed last time. So today we are going to discuss a very beautiful topic today, which is DFT, or Discrete Fourier Transform. The DFT, also known as DFT, or Discrete Fourier transform. Yeah. Here we are introducing a new word of what we have never been using, which is Fourier. Fourier is a Frenchman who invented all these calculations, and he tried to combine the signals from different sources and just combine together and just come up, for example, of their transformation, on how they are going to be transformed. So he's a French guy who was called Fourier. You know, French men were very intelligent. So that's what I may say. For example, remember Laplace transform also is going to be used here in case of frequency domain. You will also see the Laplace also is a French guy. Fourier is also a French guy. So these people were great mathematicians. So the guy is the one who found the way how you can bring two or more signals and you combine them and just interpret them and compute them into a final state. For example, if you are trying to find the power series, for example, just trying to divide different signals or different numbers into their classifications. So this guy was a great man, a Frenchman also, of course, and he did a wonderful job, I may say. So this is a discrete Fourier transform. It is, of course, if you say a word like Fourier, the discrete, you understand that it is going to be turned digital. So it is a digital computations to transform some of the digital signals into the hardware implementation. You want to implement hardware, you can use DFT. For example, dear students, for example, if you will be doing your projects, and here, of course, also you will have some of the portions, maybe the 6th week or 7th week. You will have to do some of the computations using DFT, also by implementing the lab, going into the lab using a MATLAB. You also have to look into that. We shall discuss about that and just enter exactly into the practical skills. So this is very important to note. So if you have a hardware implementation and you want to obtain, for example, the gloves, the diagrams, the what, signal, the graphical presentation as we saw in the first chapter, the way how signals can be presented, it is easier to obtain it by using all these computations. And one of the computations, of course, they are the DFT. So the hardware implementation is very easy. It's very important to note that this hardware implementation can be done by using this method, which is a DFT. So that is one point that we should note. Another point that we should note also, suppose, for example, just bringing together the other signals. For example, if you have the raw data or the raw signals, for example, the signal which has never been purified, it's going to be purified by using this technology, I may say, and you can also try to see the way how you can filter out the impure signals or the signals which have never been purified into their purest form or the appropriate form. So you remember we use filters. The filter also will be its own subject, but in this case, filter is very, very important. We shall look into that and see how you can design different types of filters in the next 2 chapters, for example, and see how filters behaves. But filter, their purpose or their function is going to be very important in terms of just purifying the signals. So you can evaluate, for example, the digital, using a digital filtering or ID filters or a VO filter or FI, R filter or IR filters. So it will depend the way how you will be using to filter out some of the impurest, the unpure signal to be in its purest form. That's very important. But remember, why are we trying to filter out, or what is our main purpose or the target? What are we trying to bring on the board? What do we want to see? What is our expected outcome? This is very important to know. So we are trying to see. Remember, we will have digital. Everything is becoming discrete. Everything is becoming digital. But remember, there is a way how you can convert digital form into the digital or time digital signal in their time domain to their frequency domain, as we saw. So here in this case, we want some of the response, and one of the responses the frequency responses. So you may have, for example, the signal in its time domain. Remember when we discussed some of the discrete Fourier, for example, in their time domain, for example, just putting some transform or Z transform and just getting the big X, the big X, the big X. So the big, this is going to be big X of Z. So in this case, we can, this is in its discrete form, but we want to obtain, for example, Z transform, which is in a frequency domain. So likewise, if you see, and if it is an inverse, it can also be the vice versa. It can go the other way around from this stage. So we saw some of the conversions, and here also we are going to continue with all those versions, for example. So we have there are so many things here that you should understand, dear students. For example, here we have talked about the filters that are going to filter out the impure signals into their corresponding purest form. That's number one. But also we are trying to get the output, which is a frequency response. The output, you can call it a response or the response or the output or the result in their corresponding frequency domain. But remember, which system are we using? You can even recall what we discussed, the linear time environment. So we are using the system which is LTI, which is linear time environment. So we said these systems that they are going to help us to shift some of the linear systems into their corresponding systems. Of course, we saw some of the properties of linear time invariant, being it as a system that is going to help us, having some independent variables that are going to be transformed into their purest form. So suppose if you have a system that is it's I mean the raw data or the data that has never been transformed. So you need such a system or a hardware system or a what in terms of linear time invariant that are going to put the values into their independent variables, that the terms or the values that you're going to obtain are going to depend on their own. That is the beauty of having this LTI. So that is a brief explanation of what is DFT. So we are going to discuss the DFT by just outlining some of the very important outlines here. We are going maybe to make it clear, you are going to see the outlines of DFT. We are going to discuss the tools that we use in DSP. First of all, the types of signal tools. Number one, so the outlines of this chapter is going to be the outlines. So number one is going to discuss types of signal tools. Of course, there's the DSP signals and their tools. And their tools. Number 2, we are going to discuss the DFT in general, DFT, the digital, discrete Fourier transform. We are going to discuss the inverse of it, inverse DFT. So we are going to discuss also the relationship between DFT and relationship. I can just put it in this form. That is the abbreviation between DTFT, DTFT, DTFT. So this is in their time domain discrete, time Fourier transform. Discrete time. Now we are bringing the element of time. Yeah. So we it's called their frequency. The relationship with time, that is with DFT, and also discuss about the properties of DFT. Properties of DFT. These are the outlines that we are going to discuss today. We see also examples of DFT or DFT examples. So this is chapter 3. Today we are discussing the chapter 3. So this is very important to highlight these examples. We also have to discuss what is the importance. For example, we used to see some of the derivatives, the way how, for example, if you have a trigonometric value, remember having a sine or cosine, we want to see their conversion. For example, if you have a complex value that you have to determine a real value number and an imaginary number, we saw how we convert them, having the imaginary value in its complex form, or the z polar form, into their corresponding value. So here we are going to have some of the transformation. For example, having the usefulness or the cycle value of e power j. Remember, omega is going to be transformed and become, for example, some of the 2 pi, for example, n value or k value. Once it is shifted, then over 4. We are going to see this relationship. But to just highlight, remind you, for example, if you want to calculate, for example, you will have, for example, the omega being 2 pi n or k over n, small n or big K over big N. So this one, we are going to use it throughout in our equation. So we are going also to see the matrix equations of DFT. So we are going to talk about the DFT in its matrix, DFT in its matrix form, or the matrix equation. So these are the few of the highlights, or the way how we are going to look into that, and we are going to discuss one by one. So we are going to begin with the first outline. So bear in mind that this discrete form is going to help you to compute some of the values during the hardware implementation of obtaining the purest signal from their impure signal or the other signal that have some of the the hindrances, as we said before. So convolution sum in this case, it is going to be also like the other one, but in its form, it's going to be in another form. So today we are going to now, so beginning with the first one, we are going to begin with the signals and their tools. How do we obtain, or if we want, for example, to obtain some of the signals. For example, you remember some of the types of signals. There is periodic signals, depending to their nature, there is also a periodic signals. So we are going to begin with, for example, the periodic signal. So we are going to begin with this number one of our outline. So okay. So number one, we are going to see signals and their tools. And tools. So yeah. So we begin with some of the types of signals. For example, the outline is going to be, for example, let us first discuss with a periodic signal. A periodic signal. Okay. Remember we said last time, for example, a periodic signal is the signal that is not going to follow some of the orders. For example, it can vary anytime. It doesn't have a repetition of some powers of some numbers. The numbers that is recognized, or unknown numbers will appear. So there is no known number that is going to repeat itself. So it's different from periodic signal, because the periodic signal we have some of the time intervals that are divided according to their numbers. So in this case, it can vary at any point. The periodic signal is going to vary according to their any points. So it doesn't follow some order. So it will extend some of the values, for example, from negative or infinity to positive. To infinity. It's without any. Remember, without any repetition. So it's not going to repeat from negative infinity to infinity. So in between, it's going to vary accordingly. It's going to vary from any point, not a fixed point that is going to vary. So that's why it is called a periodic signal. And for example, if we have values, for example, exponential form. For example, if we have y is equal to e power negative x. So that is the signal number one. But also you can have y, which is going to be x squared. So these signals, if you want to analyze them, you are going to use Fourier transformation. That is a tool. In this case, you are going to use, for example, Fourier transform or Fourier transformation. And this brings us to the topic today, which is very important to note that DFT is going to be the discrete value, but using a transform tool, which is called the Fourier transform FT. So in this case, if you are to analyze these signals, you use Fourier transform. And for example, if we have the signal in its frequency domain, this is big X, for example, and you want to or we have a signal like this, for example, in its digital form, or the time domain. Remember, it is an exponential value, so it's going to be, if you have your y-axis and z-axis in this case, or you have your imaginary value and your real okay, no, okay, this is the future with respect to time. So it's going to be in this case y is going to be this value. Yeah, so going to be a power n. So it's going to be, this one is x of n, and the other one is going to be a number of times that you are dividing in this case. So these are number of times. Okay, we call it this one. In case of instead of using t, you can use n in this case. So you remember exponential goes like this. For example, it can come from negative infinity to these values, for example, and you can consider some of the values here. So it's going to be value here, then value here, then value here, then value here. So here is going to be negative. So it's going to be, for example, we can begin from here, there, there. So so it is in this form. So it's going to be in this form. So you can see it is now a power n, or in it's a exponential form. So this value, if you are to analyze a signal like this, we use what we use Fourier transform. And depending to which value, for example, you can use with respect to time, that is dTft. So if you are using with respect to time, you can use dTft. Of course, this one is a word that is repeating there and there. But also you can use dFft. You can use dFft. So using purely Fourier transform. So that is very important. So I was talking about the aperiodic signal that can even change with no repetition of equal units or equal transforms. So now, if we talk about periodic signal, so and here we are going to have a repetition of some values at a fixed interval. So here is going to be considered, for example, if you have a sine wave, or remember if you have y equals to sine something of x, for example, in this case. So this is what we call a square wave, for example. So you are going to count the x values at a given interval and having the value in case, for example, remember if you have a square wave in this case, so you can have a square wave in this form. So you can have a square wave in this form. So it is fixed at any interval, bringing some digitized formation of a sine wave. Instead of having this, the values of just it's an analog form, or it's wandering signal, or just the continuous signal, then you can have a discrete value of a square wave, for example, in this case. So you can see this square wave can be determined according to their values, for example, in this case. So this is very important. So first of all, we discussed about a periodic signal which doesn't have a fixed value at any interval. That is number one. And we saw it can happen at any particular point. So in this case, you can never know, or you can never determine which side is going to be the actual point that you're going to fix your value. So this is a periodic signal. The importance, I mean, the example you can see, but here you can easily determine. So if you are determining, remember, The other zeros are being 0, 1, 0, 1, 0, 1, 0, 1, and so on and so forth. So depending to your numbering system or the values that you can obtain from your numbering system, you can obtain. So the other one was, the tool that we used here was Fourier transform tool. So for example, if I say, for example, if I ask you, please, students, okay, it's a question, for example, that may come in your exam or the card. I say, discuss different types of signals with their tools, for example. That one also can happen. So you remember, if you say a periodic, you can easily remember, it comes in your mind, and just think of Fourier transform that's going to analyze all these computation in case of exponential values. So in this case, so you will tell me a periodic signal, you give an example, then you give a corresponding tool. Then I will be happy and just make it, I just give you your marks, full marks. But suppose if you don't know even what is a tool, what tool do we use, it means you didn't catch up during our classes or our sessions that we discuss in this case. So remember, all these sessions are there to help you to know the various technologies that we can use during analysis of these tools. So this is a Fourier transform for a periodic signal, but in this case it's going to be Fourier series. So the analysis tool is going to be the tool, analysis tool in this case, and this also is going to be a tool for a periodic signal, and this is going to be the tool for periodic signal. So this is what we use to get square waves. So it's very important to note this. So we have seen a periodic and periodic signals, but in which form? They may come, for example, a periodic discrete, a periodic if it's for a complex value or frequency domain, a periodic in which sense? For example, as I mentioned, some of the relationship that we discussed. So now we are going to see when it is a periodic in terms of discrete, for example. So we are going to discuss about, so if it is, for example, a periodic with discrete format. So in this case, the analysis tool is going to be using time domain in this case. So it's going to be DTFT. Remember, time, now we are bringing the element of time to compute our values. So this is a tool that we are going to use. So the analysis tool for this periodic discrete is going to be DTFT. So remember, now this one also is a tool. We have seen DFT, Fourier series as a tool. Now we are coming up to some of the signals here. Okay. I hope you understand. Aren't you? So it's just a repetition of just reading from the handouts I will be giving you. Also reminding you to subscribe, share, and just likes, so that every time when I upload all these videos, we easily see them. Also, you will use also my email. If you can recall very well where I wrote my email, you can send me any doubt, then I can give you some of the clarifications. But also remember to give some of the comments here, because comments are meant to make me improve. They can make me improve. What do you think can make you better understanding of this course? What do you think that can be improved during my teaching? And what do you think I should stop doing, or what I should just strengthen, or just put more emphasis? And what do you think I should just stop doing? So there are three main things when in my teaching methodology. First of all, I would appreciate from your comments what should we do to make our subject interactive, and what do you think I should improve, and what do you think I should also stop doing, because I'm here to help you, and also it doesn't make sense to do something that annoys you or just discusses everyone, because we are trying to make everything better so that we can have understanding. So this is very important. So please, those comments are going to help me to improve the way where to improve my weaknesses, and so where I can put some of the strengths and just make this course very useful. So all those communications can be very useful in this course.